the last lesson, we learned how to program recursive functions that calculate with integers. We learned how to use invariant programming to make these functions efficient, so they are exactly loops. But integers are a rather simple data type. We would like to make calculations with many integers at a time. We would like to write functions that calculate with large, huge amounts of data, thousands, millions, billions of integers. Okay. In order to do this, we need to introduce a new idea. We need to be able to define compound data types that combine many other data type values into a single compound value. One of the first and still most useful compound data types that was invented is the list. A list is an ordered collection of elements, first, second, third, and so forth. Lists are the fundamental type in the symbolic language Lisp, list processor, invented in the 1950s. By the way, a symbolic language is a language that can calculate with data that are not numbers. For example, with lists, with trees, with graphs, with any kind of data that is not a number. We can use lists in Oz. So let me show an example. Let me declare here the identifier x, whose variable in memory will be bound to a list. So here I write down a list of 3 elements, 1, 2, 3, using the bracket notation. So I can browse x, and the browser is able to understand this, knows about lists, and can display them. Okay, we can calculate with lists too. So for example, here let me call a function, append. This is a built-in function in the system with 2 arguments, x and x. And what this function does is it calculates a new list whose elements are first the elements of the first argument and then follow that the elements of the second argument. So I do browse of y here, and I get 1, 2, 3, 1, 2, 3, so the list of 6 elements. So you see that we can calculate with lists. We can write down lists, and we return the list values. Note that the value of x here, if I display it, is not changed. In fact, the call to append has not changed x. In fact, x cannot be changed. The value of the list 1, 2, 3 cannot be changed. So lists in memory are in fact constants. They are values constants. Just like the constant 23, the integer 23 is 23 and cannot change. Lists have the same property. The list 1, 2, 3 is the list 1, 2, 3. It cannot change. This is another consequence of the functional paradigm. Integers, variables that can only be bound to one value, and for lists the same thing holds. If we want a new list, we cannot change an existing list. We have to calculate a new list. This is all nice. This is an introduction, rather informal, to what lists are. But in fact, I haven't really told you precisely what a list is, what it can do, what it cannot do, what is the efficiency of list operations, how really is it represented in the system. For that, we have to be more precise.